Back to the shop. For the longest time I wanted a squareness comparator to measure the squareness of workpieces on the surface plate. And I was thinking about a good design for quite some time, and due to a post on Instagram I got good inspiration on a design that looked very similar to this one, and I modified it slightly and I built it, and that's the result. That's my Squareness Comparator. It has a base with 4 feet, the hardened bumper piece with the large radius here, indicator holder up here with the fine adjustment, and a spring steel flexure in here as a hinge, and it holds my 0.002 of a millimeter MAR dial test indicator. Unfortunately, I lost a lot of video footage, especially that footage when I machined the base. Due to stupidity of mine, I copied the files back and forth between card, PC, different folders, external hard drive, and yeah, I don't find it anymore. But I have some footage left, and I will try to show you at least some of the parts as they were made. So hope you can still enjoy this video, and sorry in advance if it looks if it's a bit out of order. So have fun. Okay, this is how the Squareness Comparator looks right now. I have the base, piece of tool steel. I have 4 balls pressed into the base. The surface ground flat, so we have 4 hardened feet. And yes, I know 3 feet are more stable than 4, but so if I put 3 feet in here, it's very easy to tip over the axis between the 3 points, and I don't want that, so I went with 4. And as they are surface ground in one setup, they are all the same height, and I cannot measure any tipping on the surface plate, so spare me that comment, please. I have the clamp here, which this is a piece of hardened ground linear shafting. I have the clamp here, bored to a close fit. I reduced the material cross section here and here by putting this radius in here, so the clamp works very easily. In fact, I even can lock it by just pressing on here with my fingers. And it's a 2-part design. I have the clamp and the indicator holder as a 2-parter. There is a split line, and I have a piece of spring steel, flat spring steel 1mm thickness as a hinge. And I have an adjustment screw here, and the screw presses down on the movable part and bends the flexure here, so we can very finely adjust the dial test indicator. The holder for the dial test indicator is, I milled a dovetail, 60-degree dovetail, 5mm, and split it, and it's also clamped with a single screw. So I can hold my regular dial test indicators. Of course, I'm going to make some proper screws, thumb screws, for clamping and adjustment. Let's take this guy off here, and the clamp off, and I have a lot of photographs that with a write-up that I will link to in the description. take off the indicator holder. It's screwed on with two 3mm screws. And as you can see, I drilled also into this piece and pressed in a ball bearing ball and then surface grounded. And that gave me a hardened wear pad or sliding surface for the adjustment screw. So I don't have to harden the whole part. Just drill 1 or 2/10 of a millimeter undersize, press in the bearing ball with some Loctite, and surface grind it flat, or if you want. So that's current current state of progress. Now we will proceed on. Okay, the last piece we need for our Squareness Comparator is the bumper, which goes here. We will drill and tap 2 holes into this face so we can screw it on here. And I like the bumper design with a big radius. And we're going to mill it out of a piece of tool steel. It will have an L cross section, L shape, and have a big radius milled onto it. I have to do the math which radius we will end up with. Then we will harden it, then we will grind it, and we will hard mill the radius just to clean it up. I have no way to grind such a big radius on my surface grinder properly. I know that you can side wheel such a radius freehand with the magnet turned off, but I think I prefer hard milling and then some handwork with stones to even it out. So let's go to the milling machine, take this piece of 120A tool steel and make some chips. And we start machining the bumper by squaring up the piece of tool steel with a rather small 6mm carbide end mill, just surfacing down both sides, both saw cut sides. The other 2 surfaces are already pre-ground, as it is pre-ground tool steel. And I prefer the smaller end mills for such tough materials, as they don't tend to put as much strain on the machine as a big cutter would do. Of course, we do all the machining dry, except for squaring up the ends, because I'm using a 8mm high-speed steel end mill and I don't want to run that without any lubrication on tool steel. So I'm using a little bit of cutting oil. Deburring the part, I'm of the mindset to not chamfer the edges while you do machining. Only remove the burrs by moving the part over some emery cloth. I have emery cloth double stick taped to a old parallel. That's what I use for deburring. And roughing out the L shape, again with the 6mm carbide end mill, and I'm using some compressed air to get away the chips. I'm running at 1000 RPM and about 1.5mm step over, with full depth of cut, which is about 10 or 12 millimeters. And this is very easy on the tool. You use the whole length of the flutes, and that's how you get more life out of an end mill. And taking the finishing cut. Now it's time to clean up the mill, and the real advantage when you do dry machining is that you can just use your shop vac suck up all the chips, and you're good for the next setup within a few seconds. Doesn't really take much. And again, deburring the part, not chamfering any of the edges right now. Just knocking down the burrs. I'm referring to the Mechanical Metal Trades Handbook to figure out the radius of the bumper. A bit of math. But before I machine the radius, I'm drilling the mounting holes into the bumper. Spot drilling, and chamfering the holes. And I get asked a lot what cutting oil I'm using. I use whatever I can get my hands on, and right now I'm using this Cron oil. Getting the rotary table ready on the table to do some radius milling. And always careful when you set up machine tools not to dent your machine's table or the tooling itself. Careful, lift it, slide it in place. And now we're setting up for the radius milling. I have the part back there on a parallel. Slightly tucked down with one strap clamp, and now I'm using a stack of gauge blocks to get the right distance to the center of the rotary table. I have a 6mm high-speed steel blank in the collet in the center of the rotary table, and that's my reference point for aligning the part. And I'm using a square to get the part into the right orientation in the other direction. That's a bit fiddly, but it doesn't need to be super accurate for this purpose. And attaching a second strap clamp, tucking it down, and good to go. Very easy setup. 4mm carbide end mill, and we're cutting the radius in about 0.5mm increments. I don't want to overstrain this setup. And I didn't mill all the way through. I left about 0.1mm of material in the end, so I don't run into the danger of machining into my parallels. And that's how the part looks right now. We have the remaining material still on there. Clean off the rotary table, a little bit of compressed air, and tear down the setup. That's our part, and we can easily break off the remaining material, and yeah, that's the radius. Okay, we're over at the benchwise, and I'm using some hand files to clean up the radius before I harden the parts. Just a fine triangular file, cleaned up most of the milling marks. And look at the mess on my bench. This is the finished part, and now it needs to be hardened. And the great irony is I have an oven, and a very kind viewer sent me a Eurotherm temperature controller. It's right there, sitting already in a box, but I didn't have time to wire it up and make it running. So for this part I have to resort to the torch. Running my small oxy-fuel torch with the biggest tip I have to harden the part. It's absolutely not ideal for this part. The part is almost too big to be hardened with this torch, but it worked out in the end. Took quite some time to get enough heat into the part. You can see I'm slowly heating it up to a cherry red temperature or color. And as this 2080 tool steel is air hardening, you can air harden or oil harden it. And I decided to try air hardening this time. So going away with the torch, and I pick up my air gun and I'm cooling down the part with air. And this should be enough to let it jump to a significant hardness. So this is a first for me. I never tried this before, so we'll see how it works out. Okay, you saw me just flame hardening the part, and I wanted to know about the hardness, at least approximately. And I have the set of Tsubos and hardness testing files. I ordered these directly in Japan because they're cheaper that way. You can find them on eBay when you search that name. Made in Japan. And Tom Lipton already showed them, so I won't go into great detail, but they are quite neat. It's a set of 6 files and they range from 65 Rockwell hardness C, that's hardness with a cone, 65 down to 40. And you use them to test the hardness of a workpiece. You start with the 65 HRC file and you just press down on the part and see if it grabs. You don't take big filing strokes with this. You just look if it grabs. And if it grabs, like the 65, you take the next softer file, 60. This grabs too. 55. Barely, or almost slipping. 55. This is 50. See, no way. Doesn't grab at all. Just scratches the scaling. So 50 slips. 55 grabs. So hardness between 55 and 50 without tempering, annealing. So I won't do anything to the hardness of the steel. The flame hardening is not the most ideal choice for this part, but I decided to go with it instead of firing up the oven and waiting 1 hour until it's up to temperature. So now as the part is hard, we can remove the scaling. I removed the scaling before grinding because it tends to glaze up the wheel. Okay, we're over at the surface grinder and I'm just touching up all the surfaces slightly with an 80 grit aluminum oxide wheel to get the part after hardening nice and square. Or back square again. It was square when I milled it, but hardening of course slightly warped it. And I'm not too fuzzy about the dimensions of this part, I just want it to be cleaned up and nice and square. But even that would not really matter, but my personal OCD doesn't allow for parts that are out of square. So cleaning it up. So, and I'm using some oil for grinding. I'm still experimenting around with different coolants and lubricants for surface grinding. I tried Windex, I tried soluble oil, I tried whey oil, I tried cutting oil, and they all work almost the same. I can't really make out much of a difference except for the mess they produce. The soluble oil, of course, gets everywhere on the machine, and the machine is not built for wet grinding, so I'm not sure how I'm going to do that in future. Here I'm facing off the ends of the bumper just to clean them up, and as you can see it's blocked in with 1 to 3 blocks and held in place with a canned twist clamp. Okay, checking the clearance for hard milling the radius, and as you can see, I just broke my carbide end mill by running it into the parallel with the spindle not running. Back with a new carbide end mill, hard milling the radius, 50 HRC hardness, 1000 RPM, full depth of cut and little step over. And this left me with a very fine surface finish. Changing to a carbide chamfering end mill, cutting a nice 45-degree chamfer on top of the radius. Same here, running at 1000 RPM and stepping over about 0.2 millimeters per pass. Going over to the workbench, clamp it on the vise, and I will use an assortment of stones to clean up the radius. I will start with normal aluminum oxide stone and then finish it with a very fine ruby stone. Those are used normally by tool and die makers for polishing surfaces, and they are the best stones you can get. They last a lifetime. They leave a very good surface finish, they don't break down, and they are horribly expensive. So the base needs, of course, two mounting holes for the bumper. That's what we're going to do on the milling machine now, setting up for drilling into the face. Using a 3.3 millimeter drill for a 4 millimeter tapped hole. Using precision depth stop, of course. It's still working very well. And drilling the second hole. Changing to a 4 millimeter M4 tap, that's 4 millimeter nominal diameter, running at 95 RPM and slowly going down. A bit more, and reverse it out. Of course, you have to be careful when you do this. You absolutely need to watch your depth, otherwise you will end up with a broken tap. And I don't run it down all the way to a hard stop. I stay away 0.5 millimeters. Okay, we're over at the bench, and as you can see, I took some black oxide finishing to these parts, and I just buy the cheapest of these selenium dioxide bluing compounds on eBay, which has dead fish in it, and I tried various, and they all work more or less the same bad. I mix it. I dilute it with about 25% of purified water, so I get a bit more out of it, and it still works pretty good. As you can see, even on these tool steels I used for these parts, I get a pretty good finish. It's not a deep black, but it's an okay finish, and it will over time get a nice wear on the edges and look used. In my collection of screws and thumb screws and stuff, I found this nice big 6mm threaded knurled screw, which works very nice as a adjuster screw for the fine adjustment of the dial test indicator. And what we're going to do is we're going to face off the end, drill it out and press in a hardened steel ball. So we have a hardened surface running on a hardened surface, and that should give a very fine and precise action for the adjustment. So let's go to the lathe and drill this out. Okay, off camera I drilled the end of the screw to 3.9mm and pressed in the 4mm ball bearing ball, and we put this together, and you look through there, you can see that the ball tip of the screw rests very nice on the hardened pad that we put into the indicator holder itself. And now with the screw we have with the two hardened surfaces sliding on each other, we have a very precise and very fine adjustment for the indicator holder. And as you can see, I put some preload into the leaf spring. I bent it over slightly, just in the vise, and hammered it over a few degrees. So I have some preload already there. And when we put this all together like this, and it should, yeah, there you go. And with the indicator in here, now we have a very nice Squareness Comparator. We will blacken the base too, and I will make some thumb screws here and here. So let's go to work. Okay, I did a lot of work off camera because it's always the same. I turned the two knurled screws and put it all together. And I blackened the base too. As you can see, it didn't came out too bad. Looks okay. Now it's not very even, the black, but it's a nice color for itself, and it matches the other parts. And as you can see, I can lock this with 2 fingers. So that's a sign of a hint of precision. The bore for the clamp is pretty precise. The cross section of material has the right dimension, and the threaded hole for the screw is in the right position, so I get enough leverage by a minimum of torque for some proper holding force. And the fine adjustment in front here works also very well. The feedback from the screw is very nice. With the hardened ball running on the hardened surface of the wear pad in there, you don't get any stickiness is the term, or raggedy movement or something like that. It's just a nice action there. So let's go to the surface plate, and I will show you how this thing works. Okay, I brought the indicator up against my reference square, and I searched for the high spot that's there, and I zeroed out the dial. And this is a 0.002 of a millimeter per division indicator. That's about 1/10,000th of an inch. So now we have our 0, and I know that the square is square, and we can take stuff out of the shop and check it for squareness. For example, we can take my good Japanese grinding vise and check if this side is square to this side. Let's drop it on the surface plate and bring the Squareness Comparator in contact and swivel it across to search the high spot. And as you can see, we read pretty much 0. And that's what I expected from this slice. We could also check my hand-scraped toolmaker's block. This should be square to about 5,000th of a millimeter. That's a nice sound. Let's see. Yeah, this is 0. This is 0. Here we are minus 4,000. So that means it's tipped away from the gauge. This side is plus 4. Always keep in mind, plus, on this side it's plus 2,000. Here it's also plus 4, plus 2, sorry. And here it's 0. So this block is pretty good. This is out of the beginnings of my scraping career. So that's the